welcome everyone. First of all, I just want to say that we are thrilled to be here, and I would like to thank the ADC organization for this amazing event and the opportunity to talk with you today. And I would like to thank you for being here also. So welcome to this talk about real-time audio separation on iOS devices using AI and deep learning. So who are we? This is Clément. I am Adrien. We work at MWM. It's an app development company based in France, close to Paris. We used to work on audio-oriented applications such as edjing, which is the #1 DJ app on mobile platform. But now we develop all kinds of creative apps, drawing app, video editing, in addition to music application. An audio signal processing R&D team was created in 2015, and more recently, a machine learning R&D team was founded in 2019. Today, both teams work together hand in hand, and this talk is a good example of signal and machine learning collaboration. And for the record, I work in the audio R&D team and Clément in the ML team. So why do we want to run an audio separation model in real time on mobile apps? We could do it on server side. That will allow us to use unlimited resources, but at the cost of a consequent waiting time, and also it can be very expensive to run models on dedicated servers. And that's why we decided to focus on real-time separation.
So hello, my name is Clément, and I'm the deep learning guy in our duo. So today our presentation will fall into 4 parts. First, I'll give a brief overview of how deep learning works in general and how it applies to source separation in particular. Then Adrien will explain the stakes of its real-time implementation on mobile devices. Then I'll go through some of the experiments we run for the source separation before showcasing some concrete apps that we develop at MWM. So let's dive in for the first part. So for those who are not really familiar with deep learning and how it works, just let you know that deep learning is a subfield of machine learning. And basically, we design neural networks. And here we'll focus on the supervised way. So we, beforehand, collect and gather data set, a collection of items with mixture as an input, and the associated label will be the stem. So with these neural networks in mind, it's basically like a bunch of mathematical operations with lots of parameters. You will see this as a function. And we'll try to optimize those parameters during the training phase. We give ourselves an optimization criterion, and we iteratively update those parameters so that the model will, when given an input mixture, output the associated stem. When we are done with the training phase, then we validate it. So we give ourselves some metrics. We compute them on unseen data. If the model generalizes well on this unseen data, we are done. So on the particular setup of source separation, here we assume that the mixture is a sum of its stems. So basically, it's generally decomposed into 4 or 6 stems. Here we have vocals, drums, bass, piano, guitar, and the rest, we call it other. So the network will be input the mixture, either raw waveform or pre-processed, and then the same is applied at the end of the neural network with the post-processor to give the raw waveform back for the stem. So in our case of the training, we collected 10,000 tracks. This is a private data set with the mixtures and the associated stems in CD audio quality and stereo. And we worked in the 6-stem setup that I just told about earlier. To validate the quality of the source separation, we use a common public dataset, the MuseDB, as well as a private one. And we use some metrics, so you may be familiar with the signal-to-noise ratio, as well as the mean absolute error. And we also assess the quality of the source separation with our own ears, because some metrics do not really describe perfectly the quality of separation. You may have like some leaks or screeching noise sometimes, and it doesn't like translate in the quantitative metrics. So bear in mind that those two were used to assess the quality of our model. So then, when we are done training and designing our neural networks, we need to make them run on mobile. So here we focus on iOS devices, and we use the framework developed by Apple in 2017 called CoreML. It allows us to run on the different chips embedded in the iPhone. Actually, the CPU, which is the slowest, then the GPU, which is faster, and then the ANE. ANE stands for Apple Neural Engine, and this is the fastest of the three. Actually, there is a drawback for this. ANE has a limited support of the operations I talked about earlier, the layers in the model. So it's basically a trade-off between the layers we want to use in our network and the speed up you gain using the ANE. So this is there's also another problem. This is the CPU fallback. Sometimes the layers are supported, but one is not, and so you have like some speed cost. We need to get by those constraints to make the model run in overall good speed.
Yeah, so now we are going to talk about a concrete real-time example on device. So developing a real-time model embedded on device brings out a lot of difficulty. They are constrained from the device audio loop, constrained from the size of the model, because the app size should not be too large in the mobile world. They are constrained from the model type according to the device type. As just Clément said, some devices don't have ANE chip, so ANE model won't run on non-ANE devices. And plus, models should not run on GPU because it may affect user experience, such as low graphic frame rate if GPU is overloaded by the model. And also on mobile phone, GPU is not available when the app runs in background. So a GPU is not an option. And of course, with all these constraints, we still want to have a very good separation quality. So we want to be at the state of the art for audio separation. So this is a standard audio thread behavior, an example of audio thread behavior. The audio thread is in orange. It is run by the device. We don't control it. The audio buffer, you can see here, is provided by the system, and it must be filled before the call of the next audio callback. So for multiple reasons, we cannot run the separation on the audio thread. There are risks of going beyond the allowed duration. And CoreML methods contains allocations and lock, and it's forbidden to use them on the audio thread. So we need to run another thread, the separation thread. It's the green one, on which the separation will be processed. And separated data are given to a thread share object, which is in the middle, the cached separated audio data, providing the audio loop when necessary. And of course, with this kind of thread share object, extra care must be taken about these objects because it is shared between two threads. So I'm not going to explain it in detail, but Timur Dumler will explain it much better than me. So basically, the separation thread should be fast enough to provide the separated data to the audio thread. I'm just going to dive a little bit in this module, the prediction, which is the heart of the separation. Actually, the raw ML separation itself, it's just a call to the core ML API, and this is what is done in the middle here. But before and after, there are a lot of work. There are a lot of pre and post processing, like FFT, spectrograms, data alignment that are specific to models. And this kind of pre and post processing we coded ourselves. It was a huge work, and of course, these processing phases must be optimized to run as fast as possible. So if we sum up the constraints, of course, the audio separation of 1 second must take less than 1 second to be processed. Latency must be as short as possible. For example, if the... This is my app, yeah. for example, if the input audio chunk is 30 seconds and we separate it in 25 seconds, the real-time ratio is below 1, so it's okay. We are faster than the separation, but we still have to wait 25 seconds to accept the first frames of the separated data, and this is too long. So we still need to have a good reactivity, and the latency of the model must be as short as possible. And of course, we must have a CPU or ANE load that should be reasonable to avoid device heating, for example. And so we needed a tool to monitor all these constraints. Whenever Clément did a model, we needed to know which constraints were. Well, we needed to see each data of this constraint, and this is why we built an app. We built an in-house benchmark tool, which is an app, and I will describe in the next slide. So in this tool, I'm going to show you. So in this tool, we load the model, and we run looped dummy predictions, and we check the constraints. So here you can see, just before I press play, the name here is the name of the model, Dune, TFC, DTF. It's a model, standard model. In this video, it was made on an iPhone with ANE chip. And in this tool, we can choose to run the model on CPU only, CPU and GPU, and all meaning ANE and CPU. And these are the constraints that we can check. So for example, if we run this model, the Dune model, on CPU only, you can see, come on, okay. You can see that, so I'm just gonna pause it. The CPU load is very huge, 100%. This is not acceptable. The prediction time is pretty high, but you don't have a reference, but it's pretty high. And more importantly, the real-time ratio is 1.26. That means to separate 1 second of data, it takes 1.26 seconds, so the real time is not possible here. And I'm going to show you that if we switch just above, so we are CPU only up, we switch to all, and here you can see the new data of the same model running on ANE. So the CPU drops down to 52%, so this is much more acceptable. So we still have 50% on CPU. Why? Because some operations don't run on ANE chip, so we still have fallback sometimes from ANE to CPU. So this is why we still have 52%, but 52% may be acceptable. And the real-time ratio is 0.12. That means this is much more acceptable. And with this kind of model on ANE, we are able to run a real-time separation. So this tool is pretty useful, and we used it to design all our models. Okay, now let's move on with the...
Yeah, let's move on to the network cooking part. So first of all, just to remind you that the vast majority of the source separation models fall into 2 categories. Either you input them raw waveform and they will output raw waveforms as well, or you use spectrogram-based model and you use the STFT as input and they output STFT as well. And these second types of models are more common, and usually the flow goes that way. First, you compute the magnitude and the phase of the input mixture. You discard temporarily the phase and you focus on the magnitude that you will input to the model, which then will estimate a mask. So each time frequency bin is between 0 and 1, and you will multiply them element-wise with the magnitude of the input mixture to get the magnitude, the estimated magnitude of the stem. And then you will reuse the phase of the mixture, and you invert the spectrogram and get the raw waveform of your stem. So this is like a common heuristic, and it works surprisingly well to reuse the phase of the mixture. So for our first example, we tried to wrap a splitter. Splitter is a really popular framework developed by Deezer. It follows the flow I just talked about in the previous slide. And basically, it's like for the deep learners, it's a convolutional unit. It's really convenient because it was pre-trained on a large data set, like 20,000, I guess. And it comes like with a few configurations, for example, the 4 or 5 stems, so piano, guitar, drums, bass, and vocals. It's really, really fast on the A&E chip, and it works like only on A&E. There is no CPU fallback, so very cool to get that, and it's robust to most musical genres. However, we have some drawbacks for this model. It's quite heavy. If you want to develop a mobile app, you have to embed 75 megabytes in it, and it can be something to bear in mind, as well as some source separation quality issues. You may have tried it before. It has some phase artifacts and shows like muffled sound, especially for drums, for example. And when we tried to use this model for like low, old iPhones, I would say, below the iPhone 8, we had some crashes. So I guess the model wasn't really performing on that range of iPhone. So we draw the conclusion that this model was like suitable, but the same as the contenders. So we wanted to make our own. So then we went for the other type, the other category of models. So djing, this time, is a raw waveform-based model. It was developed by Meta AI. It's really popular. So we went for this one. However, the pre-train is way too huge, like 2 gigabytes. So we retrained ourselves and modified some of the architecture components to make it real-time and streamable. Once we got that far, it was now real-time on all iPhone CPUs. So first victory. And the SNR, so the metric we use to compute the separation quality, was on par with Splitter, with less muffled sound and better drums. However, we didn't take advantage of the A&E itself. So we have layers here, like the LSTM, for example, and the convolution that are in the encoding and decoding blocks are force-threaded, and this doesn't work on A&E, actually. We also have some quality issues. We have more leaks with this model, actually. So in conclusion, it's good for the older phones. It will replace Splitter. However, there's still too many leaks, and we don't take advantage of the A&E. So we went back then to the spectrogram-based models. So we went for a Splitter-like architecture. Two main improvement directions were done. First, on the architecture itself, so I won't dive into much detail, but we merged some of the tweaks in the latest paper and add some new layers, for example, this one, to enhance the expressivity along the time frequency axis and get better source separation. Actually, we wrapped all stems in only one model, as opposed to Splitter. It allows to share more information in the musical decomposition of the stems. And the second improvement was more on the signal processing approach. We first, we didn't use directly the magnitude spectrogram. We first sliced it in 4, actually, and then concatenate the slices along the frequency dimension to concatenate it in the channel dimension. And this does not decrease much the performance of the source separation, but make it really faster. And the second one is, instead of outputting, like before, the magnitude mask of the desired stem, we output like some intermediate features. I won't explain the equations, but those 4, for example, was a paper developed by Biden 2 years ago. When combined, you get a better approximation of the phase and the mixture of your stem. So this all combined made possible to get state-of-the-art source separation quality with a model that is not that big, but fast enough and works for all 6 stems in the same time. So here I just like summed up all the explanations from before in a benchmark table. You can see the Splitter. This is the pre-train given by Deezer. The djing is the one retrained in-house, so a smaller one compared to the pre-trained one. And those are the spectrogram-based model that I showed you before. So I called them dense units, the generic name, whatever, and a light version of this one to make it even faster for older phones. You can see that there is like a good improvement on the SNR, so it's not SISNR, whatever, it's just a different variant of the metrics. And the model size is way better with now the dense unit. You get more flops actually, but it's compensated because you run them mostly on the A&E now. So you are a winner in this trade-off. And because it's in-house, you have like access to new stems, for example, piano and guitar that were not accessible, for example, for Gmux, and you get only piano with splitter. So in the end, we had like two versions of the same architecture, one that runs for all iPhones and one that take the most advantage of the A&E. And the source separation is now better than the things you can get online.
Okay, so now we are going to show you some concrete application of the separation in our app, edjing, and our app Stemz. So edjing is our flagship DJ app. With audio separation, we can replace the traditional EQ with low, mid, high with a smart EQ, what we call the smart EQ, controlling the volume of each instrument in real time. Okay, so this was an example in edjing, sorry. Whoa. And this is Stemz. It's our latest music app integrating this technology. It is made for musicians who want to practice their instruments or sing on their favorite tracks. You can still control the volume of each instrument. It looks like this.
Police arrest this girl, Hitler.
So yeah, so this is pretty powerful if you want to practice an instrument or if you want to do a karaoke, for example. And feel free to, you can test this app at our stand. I know some of you already did, but feel free to come to us, the MWM stand, to test the app. Okay. Okay. In conclusion, so we managed to create a spectrogram-based model, and they do the job in real time on mobile. Models are fast, or small, and real time. And what are the next steps? Of course, we still can improve the quality of the separation, especially, for example, for the bass. I'm sure we can improve it. We can still improve it. We can support more instruments, for example, backing vocals, brass, or other instruments. And we can make lighter models for slower phones and other OS also. The next step would be to integrate it on Android also. Thank you very much, and don't hesitate to go to the MWM stand, and we are still hiring if some of you are interested to come to our company. Thank you.
Hi, thanks for the talk. I used to work in a company which was doing exactly the same thing with your source separation, and one of our concern was shipping the actual network in the user application, because we were kind of afraid at some point that people could extract and reverse engineer part of our network, which was kind of say the heart of the technology. And I'm curious, how do you deal with that? Is that a concern for you? Is that not a concern anymore since how the, let's say, the deep learning stage evolved so quickly these past years? Is that a question that you ask yourself when you ship such things?
Okay. Okay, thank you for the question. Did the company work on mobile app or PC app?
No, we considered mobile app, but at the moment we were considering it only Apple, because would have the power to harness that.
Okay.
It wasn't really interesting for us. We mainly worked on desktop.
Okay. Actually, on mobile app, I think it's much more difficult to extract the model and do a reverse engineering. So we didn't think it was necessary to hide it or to do something, because on mobile app it's pretty difficult to do this. And I don't know.
It comes encrypted, I guess.
It
has the option to encrypt the models.
Okay.
So I guess it's already compliant.
When you embed the model in the app in CoreML, it encrypts it automatically.
You get the option, yeah.
I think for the talk was pretty good.
Thank you.
Test. Thank you for the talk. I've noticed in your demos that the source separation seemed to be working better for less distorted material. Is it a common observation you made, or so? For example, in the Green Day track, you could hear a lot more artifacts when you did the source separation, as opposed to the Radiohead track. Was it just because you used different models for those, or is it a general?
No, it's the same model. I think it's because on saturated guitars you have a lot of high-end frequency, and phase artifacts you can hear them more on high-end frequency. This is why you may think there is more artifacts on the Green Day than the Radiohead. But no, it's the same model. It's the same model.
Okay, thank you for the talk. So my question is perhaps very specific. What is the smallest audio block you need to feed into your model? And continue on this question, do you think the source separation on live audio is achievable? Thank you.
What was the first question, excuse me?
What is the smallest audio block you need to feed into your model, like in time? 1 second, 2 seconds, 3 seconds?
Well, actually...
Depends on the model, actually. The one we shipped in the app, I guess the chunk is about 1 second, I guess, yeah, 1 second. But when we went for the waveform-based model, like DMAX, we went way smaller. I guess the chunk was like 200 milliseconds, I don't really recall, because we upgraded to the spectrogram-based one. And I guess if you want to go even smaller, you get like some padding artifacts because of the size of the chunk. So it's always better to get a bigger chunk. So it wasn't really a goal in itself to go for a smaller chunk. And the quality decreases a bit, so you need to add like overwork about padding and overlapping. But the good like trade-off would be less than a second, and not really a concern about that. Yeah.
And also, the smaller the chunk are, the higher the CPU loads is. So it's good to have small chunks because the reactivity is better, but the CPU may be very high, so it's a trade-off.
Thank you for the speech, guys. A question. I've seen in noise suppression models, people also predict not just magnitude, but also phase of the signal. And if I understood correctly from your talk, you just use the original phase from the spectrum.
Actually, it's the splitter model that uses the phase of the mixture. And we went for different configurations. Sometimes we directly use as input and predict as output like the real and imaginary part of the STFT. We went for the magnitude phase duality as well. And we went for the, like in this slide where we showcase like 4 outputs, like some, because you need to make a ratio match that is complex, so you can't have like really a 0-1 bin. And so you go for 4 intermediate feature representations that you then combine to get the mixture, the phase and the magnitude. So yeah, you predict them.
I see, okay, just implicitly. Yeah. Cool.
Yeah, and on the splitter model, one of the bad aspects of a splitter is that there is a lot of phase artifacts coming from the fact that we use the phase of the original signal. But surprisingly, it works pretty well using the phase of the same signal. You apply it to the base and it works. When I first saw that, I was, why? Why? You will take this phase, there is nothing to do between both phases, but it works.
All right, let's give him a round of applause.